Hello, everybody. Good afternoon. Welcome to the Cruise Learning Lab number 20. Yeah, that's our 10th anniversary. And this is a new format that we are doing. We are using this webinar format now. So you won't be able to actually talk, but you can ask questions in the Q&A. So me and Daniel are going to be answering all the questions while David is presenting. So now we can all cue our videos, and I'm going to stop sharing my screen. Okay, again, welcome to the Learning Lab 20. Today, the presentation is going to be the XGB lithology classification lessons learned from FORCE 2020 machine learning competition. This is hosted by me, Marcelo Guarido, that I'm a data scientist and I'm the head of the Cruise Data Science Initiative. And Daniel Tread. Daniel, would you like to present yourself?
Good afternoon, everybody. I'm as a professor in at the Department of Geoscience, and I'm helping Marcelo with the Data Science Initiative.
Thank you, Daniel. And also a host and our guest presenter today is David Emery. David, would you like to present yourself?
Thank you, Marcelo. I'm retired from industry after 35 years with Husky Energy and have gone back to working with crews and actually starting a PhD program in basically looking at using machine learning for seismic interpretation.
Thank you. So I'm just going to start and explain what is the Cruise Data Science Initiative. It's a branch inside Cruise that's a consortium at the University of Calgary. But with the Cruise Data Science Initiative, we work with different types of projects that are related to geoscience, energy, and environmental for the academic and industry fields. So we do different types of work that's not only seismic, but other stuff as well. We also provide programming training in R, Python, and MATLAB that could be introductory programming trainings, as well as applications in machine learning, data science, and artificial intelligence, as well how to build apps. And we also provide those bi-weekly learning labs. So if you wanted to stay tuned, join us on the Cruise website. You can subscribe for the newsletter, or you can follow us on our YouTube, Twitter, and LinkedIn channels to stay tuned for the future events. So now we can go to our presenter. And I'm going to stop sharing.
So what I'm going to share with you today is work that Marcelo and I have done since the actual FORCE 2020 competition ended. And we're just kind of looking through what else we could get out of the data and different methods that we could have used when we were participating in the competition last year. Pretty much all of this presentation is going to concentrate on XGBoost. One of the main features for that is it really handles NaN values. You don't need to impute, which is one of the most common steps that you have to do in machine learning is fill in all the data fields. Nice thing on XGBoost is you can avoid this, and you can also provide weighting for the different sample sets. Just running you roughly through the data set. It's a North Sea data set. 98 wells were provided with petrophysical analysis. There was 10 additional wells for a leaderboard, and then there was 10 wells used for the actual competition, which was held back. The data is actually divided into two basins, and when we actually do your analysis using the raw data, the very first tree, if you're throwing everything in, is actually going to be coordinate information on the dividing and which of the two basins you're from. For this particular talk, we're going to not be using that information. We'll be going to be cutting it down. The well logs, there was a fairly good suite of logs throughout and a good analysis. As I say, 98 wells and over 1 million data samples. Likewise, they provided petrophysical analysis, the confidence within that analysis, and a group and formation, basically tops and intervals. In the lithology they provided 12 litho classes, of which they basically plotted through a series of different mineralogy, but still certain classes like shale was an amalgamation of a whole pile of different types of mineralogies. And things like sandstone were just given as one category when you could break it into lithic and feldspatic and quartz. So likewise, even there's a high degree of mineral mixing. The standard practice, of course, we were going through was looking at scaling and editing, what feature creation, imputing the data, normalizing the data. That's again something unique with XGBoost. You don't actually need to normalize the data. Weighting of classes. And in the competition, we actually ran through 4 different methods of machine learning and stack the output result. In this case, we're just actually going to be just applying the XGBoost for our solution. Example of a decision tree that is produced in XGBoost. Basically, you start with the highest correlation, and it's just basically a yes/no answer in splitting out. The interesting thing is a parameter can appear more than once within the decision tree, and not all things need to be in every tree. And so subsequent trees would actually be handling it. The unique thing is that the red lines indicate where the data actually has to be part of the test. And basically all that information is passed in that way. The other side is the false plus the NaN values. So basically all the NaNs will end up passing down a single branch to a single leaf. Generally, of course, won't have NaNs throughout. Now, the other thing that it's an ensemble method, but the unique thing is each tree actually picks up from the residuals of the previous tree, what it couldn't actually forecast. And so in this case, you end up with the residual, you start out with the next highest correlation, and then you move down and you keep on picking out. How much that residual is part of the learning rate, and the default learning rate is 1. We tested from 1 all the way down to 0.01, where there'd be very little change of the input data. That actually ends up producing the output leaves. Basically, it's an ensemble method, and each of the leaves has a role in the forecast. And in this data set, if I did 10 levels by 100 trees, you get over 100,000 leaves for only 12 classes. One of the big things that we were going through after is we used the raw data, and the raw data has a big depth trend to it. And we remove this depth trend, and statistically it actually improves the Bayesian statistics of each of the classes. There's still a high degree of overlap, and that's due to the mineralogy variation. And likewise, and we also tested through kind of balancing the classes and trying to find an optimum and looking at the difference. And we'll see that in the code when we get into the code. We're not going to include the validation. We used and investigated multiple methods of validation. The one we settled for was actually holding back wells, and looking at that, you end up with a far lower score than we will see actually in our training results today. But that is to be expected because we have a degree of overfit. So we're going to go from the raw data into our feature earning data and basically kind of look at what it does to our scores. So let's now jump over to our code. And so this code will be uploaded and you'll be able to download it from the Cruise website and be in the next couple of days. And we'll just kind of follow along through it. I've commented out a few things that will take a bit of time, and it's just basically loading it. We're going to import the data and just basically use the head command. The data provided was fairly substantial, and with all of the standard well logs, along with a lot of additional header information and drilling information. One of the nice things is you can go through and do a describe. Describe will tell you actually the number of data point counts, what its mean value, standard deviations, minimum, maximum. It's very useful in trying to look through to see how your data is actually scaled. In this, there was a few pieces of data that was alternate units, etc. They provided us with 98 wells and the lithology classification, and in the contest they actually provided what was the key for that. And we actually, because they've actually used a fairly long label, we just actually basically just reduced that to facies. And they didn't actually include the facies names. We just added that into the list. And then we actually match over into color bar and register the lithology colors so that I can call it later. When you come down and, oh, I've already run this once before, so the air logs has disappeared, but this is basically the lithology distribution. There's only, in the 7 of them, classes make up actually less than 4% of the data, and 63% of the data actually is in the shale class. This is going to actually create a whole pile of problems. And a lot of things we're looking at, particularly in the contest and work done later, is trying to figure out the balance and what's the best thing. I had actually included the warnings and just indicating it, but one of the nice things is if you actually in your code put the semicolon, you can actually eliminate this header that Patrol puts out. The logs itself has variation in coverage. Things like the shear log is less than 17% of the sample points have a shear value. The spectral gamma ray, things that are in all of the wells are things like gamma ray and facies classification. For here, you can see that these are fairly long, and because they're now redundant because we've built the facies class, just going to drop it from the analysis. Likewise, we have a confidence field, just shorten down the name of it, and we're going to actually create a weight field, which is just the inverse of that. And that's so that the high confidence, which is a value of 1, will get a full weight, and the values that it didn't provide, or a confidence of 2 or 3, will actually be taken advantage to use a weight to make it smaller. So taking a look at all the basically features that are available, this is just basically looking at the column headers in the data field. And we can also take a look at each of the plots and take a look at how each of the data set is distributed. I've, in this case, just for speed, I've just running one. This is an overlay of the input data set with its different litho class coloring on it, and the histogram distribution of each of that. Here you can see the shale has a double peak, and that's because there's basically a population shallow in the well and another population deep in the well. You'll see later after we do feature engineering that that is more in the sense of just less shale in the center part of the well. And this is actually a depth trend that's happening. Within the code itself, I have commented out being able to do a density plot because it basically takes a bit of time, but I have actually run that. And most of this data is heavily centered along the center point. And a lot of this is scatter as you get into things like the coals, which are a very small data set, but in the plot looks fairly intense. Likewise, we can take a look at where we're missing values. And this is where you're basically getting down to, and said 17, it's actually, I guess, less than 15% for the DTS. There's a whole pile of things in here which are object-oriented data. We're just going to eliminate that, such as the well name, facies, because that's what we're going to actually try to solve for, facies name, confidence and the weight, because we're just using them as other parameters, and the group information. In the actual full-in project, which has been excluded, we actually use the group, the formation, and the X and Y coordinate, i.e. giving a geological framework, and that actually has a substantial value or substantial improvement in the XGBoost results. The disadvantage is it doesn't generalize, so you can't actually remove the solution from this basin and move it to a different basin. Now within the code, if you actually click on any of the blue stuff, it will actually bring up, and you can actually very quickly take a look at, whoops. Let's just get that back in here properly. It will bring up actually all the connections and all the references. So they've all been hotkeyed in there. To go through and take a look at here, which is arbitrarily, and just for speed, I've made it just 40 trees and only 3 depths, and kept the learning rate at 1. And actually, when you run that, it should, in here, take about 20, 30 seconds. And the main reason that it's actually going relatively fast is because in the XGB's tree method, I've selected HIS. If you're actually using the auto or the exact, it's about 20 times slower. So this is generally running about 4 to 6 minutes to do actually one of the calculations. It's more accurate. We get some better numbers, and that's actually what we were using was the exact solution space. The HIS method is also very similar to the GPU HIS, which takes advantage of some of the GPU. So we're giving up a little bit of accuracy for speed. Within the code, you can use graphic viz library to actually plot out each of the individual trees. You can go in there, change the parameters for the tree. Oops. Run a different tree. So that way is, say in the full in data set, it was using the location data, then jumped into the gamma ray, and vice versa. You can go down and look at each individual trees and how it's making its decision. What's more interesting is actually go in and run the feature importance, and that will actually give you a nice summary of what pieces of information it's ended up using and how important did it find it. And in the raw data, it's getting a very good result, but you actually take a look at the top end values. It's actually all location information, all of the diagnostic log data that we would anticipate, such as the resistivity, the neutron porosity, the gamma ray, the density, they're actually showing up quite low in the importance. That's because of the machine's ability to actually overfit the data. In here, just going to create a plot of the actual wells, put it into a routine so we can call it again if needed. And I've colored it actually by the litho class. In here in the raw prediction, it is the facies as provided and actually the prediction that it calculated. It's relatively good. And as you can see in here, a pile of the logs were missing, and it just basically still manages to do an actually extreme run. The big one is, how does it actually compare to the test or the contest score? Now, their contest here, they ran actually a modified F1 type score where adjacent facies were not penalized as badly. Unfortunately, they just did the penalty side, not the positive side. And so what you'll see actually throughout my code is that I've taken the actual contest score, it's in the brackets as they were doing it, and I've actually just minused it from 1 and divided it by 2. So we'll end up relatively similar to the precision and recall or balance accuracy or F1 score, which you'll see later. One of the big things is trying to take a look at the learning rate and see if we could actually improve it. We were using the default learning rate of 1. In this case, just running through here and dropping the learning rate here down to 0.1. And yes. And then updating that prediction and taking a look at the contest score. So in this case, actually, the contest score got worse as we lowered the learning rate. It's predominantly from overfitting of the data, noting that it was actually coming up with positional data. In this case, though, when we actually take a look after we've reduced the learning rate, we'll see things like gamma rate, neutron porosity, the DT compressional, and the resistivity now showing up in the higher in the feature importance, and things like the X value, which was the highest on the pure raw data with a learning rate of 1, has been pushed down more where we believe it's appropriate. It's really, the score isn't everything. It's also thinking about where you want to put the learning rate. Oh, there's a little typo there. That should be 0.1. Fix the code. The next is actually to look at the overall performance. Again, we're using a routine in here, posting out the contest matrix, also looking at the precision, the recall, the balance accuracy, and the F1 score. Here, of course, it's just a repeat of that, and you end up with a confusion matrix of how well did it actually establish. So this is balanced for each of the individual classes, understanding that if I did a plot that isn't normalized, everything is just going to basically be showing up as shale, and everything else is going to be in the low colors. There's very few data points that are actually in the basement, and certain things in here like the tuff and coals are actually having a hard time. Dolomite is extremely poor, but this is raw data. We haven't done any type of testing. One of the simple things which you can do for looking at values is actually creating a duplicate, which is a different scaling. So instead of using slowness, velocity, using the raw resistivity, or taking the logarithm of the resistivity and run the same thing and take a look at the actual importance plot. Again, this will take us about 20-30 seconds to run this. It will pop up here and give us the importance. And in here now you're starting to see there is the resistivity, the logarithm is just slightly higher, and vice versa. In this case, the VP actually is lower than the DTC. it's a good way of looking through to see if actually a particular scalar, because they are basically dependent relationships with just slightly different scaling. And it's just basically picking a threshold number to make that yes/no answer. But it's an interesting way of checking it. The other way, of course, is doing the histogram and just looking at how each of the histogram plots. And very quickly, what you can see in here is that data actually is fairly noisy. There's a lot of random data points. And there's also, of course, a lot of things in here that we're not actually interested in. So we're just going to simplify things. I'm going to drop those temporary ones. I'm going to drop out the production kind of based stuff from the drilling and just drop out a few other things just to speed up the code for later on. We ended up rescaling all of the units just to make sure that they actually so such things as we basically just converted all of resitivities into the logarithms. For the DTC, checked for if there was metric and imperial numbers being mixed, using that just from the medium value for each of the wells. And this is all well-based, so it takes a little bit of time running through the data set because we have to scan out for each of the 98 wells independently. And we're taking advantage here that 60+% of each of the wells is just shale. So we're actually basically normalizing everything on the shale compaction to a secondary degree, the sandstone, and to a lesser extent the limestone. Likewise, the PE log had the biggest range. We're just reducing everything so that it's actually ranged between 1 and 10, looking at the capping of it, and also converting some of the density logs that weren't in grams per cc, so consistent units. And then we can just basically plot out the histogram, and now they're actually starting to look as we would expect the data. And then after we've done that scaling, we can actually take a look at, has it improved our performance? Has it changed our importance? And vice versa, we'll run down and calculate the confusion matrix. So again, we now have the gamma ray, the neutron porosity. The caliper is still ending up quite high, and the blowhole size, which is quite surprising. Certain things such as density is still fairly low, and a fair degree of redundancy. And actually our score has, because we've dropped logs, we're using all 100% of the data. The interesting thing is when we're doing the validation, which I simply have excluded here because we actually ends up taking about 4 times longer to run, and the way we were doing it has actually gone down. The validation will actually go up. And just taking a look at the well log. One of the interesting things, and we're still trying to work on it, is these small patinas that are throughout. They've been very difficult to actually pick up in the machine learning. It was in the contest one of the consistent responses. Likewise, looking at some of the chalks and some of the marls getting confused as shales or limestones. One of the big things is, of course, checking the hyperparameters. We can do that through a grid search. In this case, I've commented all of this out. The simple way within Python to comment things out, if I just go back that into code is just basically there's a command for the beginning and end. When you convert it back to a markdown, it will just look like code, just indented. Main reason it did that is that if I run it on exact, this takes actually 4 hours to go through the full grid search. It takes 40 minutes even on HIS. And it basically ends up with a number of estimators at 80 with a depth of 3. And it wants to push the learning rate up to the highest learning rate I've given it. In this case, I've capped it at 0.2. I'll have to do some initial work for doing that. And we're going to run with those statistics from this point forward. And so it'll take slightly longer because, of course, we have more estimators, but this is still only about 40 seconds to run through. We'll create the output. Take a look at the importance. And so I got about 25 seconds. Still really not a significant change. Some things like densities, and gamma ray is still being the highest one being pushed up. We'll see shortly that that's actually predominantly because of the shale being the largest class. In our confusion matrix, we've actually improved our contest score and moving everything upwards. If we take a look now at that first tree, it's actually picking out the shear log, the DTC, instead of that Y location. One of the big things on this is, which we also investigated during the contest, was looking at doing the balance or the weight of each of the classes. When you come up in there to do that, it's basically the 1 over X. Things like the basement's going to end up with extremely high weighting, and all the way down to the shale, which is going to have a less than 1 to balance things out. What that ends up looking like is basically getting a balance accuracy, and everything appears the same. Still in here, I'm going to actually divide that because this is redone the weightings, so everything's equal. I'm still going to do that same trick of using the confidence just to improve my estimator, and then take a rerun on that. What you're going to find actually is the balance accuracy will substantially improve, but the contest score actually goes way down because, of course, right now we're giving the same weight for those small classes as we did for the large classes. It ends up improving the overall balance. We substantially improve all the analytics and all of the logs that you would expect to be giving you lithology starts ending up high. You'll see now that gamma ray has fallen way down because, of course, it was way up because of the shale class. But now the contest matrix has actually gotten quite bad. When you take a look at it, it actually looks very good. Everything's very centered, and that's because the balance accuracy has gone right up, the precision's gone up, but the contest matrix actually has gone down because of the number of missing. Because you remember originally we had 98% of the shales, now we're only getting 67% of the shales correct. The other one is to do a partial balance, and for this we just basically taking it to the power, and it basically just gives a new balance or semi-balance accuracy. That's what we actually then tested on different numbers, run through, and to see what the best results was, so that we could still get the best contest results while taking advantage of the undersampling of data sets like the coals and the shocks. If you remember from the original, these were barely visible. And so we're now weighting or overscoring those things. When we come back in, we still, again, have it. Gamma ray now has come way further up. And our accuracy and our contest matrix has gone up at a slight loss of balance accuracy. That was at 81 before, it's now at 78. But overall, our overall performance has substantially improved. Still though, of course, at 82% of our shale. Now, another thing that we can do for looking at the right feature is to do a one versus the rest calculation. In this case here, I've just redisplayed each of the classes with its numbers, and we can go in here and look at any particular class. So we could just basically say, let's do the largest class, do 3, and see, run that one, look at the feature importance, and it tells me that the gamma ray and the DTC. And we could go back in there and say, okay, well, if I was instead looking for halite, and I want to look through, and all of a sudden the halite is telling me the neutron porosity is going to give me the best definition. And it's going to be, and then we can actually take a look also on a one versus the rest on what is the actual analysis. And in this case, it's basically picking out 98% and very small percentage of mispicking. Now we're just going to very quickly here, and I'm just going to select a small subset of plots. Yeah, those 5 should do fine. And just plot out what those cross plot is, because we're going to actually go in and try to remove that depth trend. We're also going to go through, because if you had noticed before that the medium depth resistivity and the deep was actually more coming out generally more important as a deep resistivity. And so we're just going to actually change things over so that we actually get the average resistivity, and then we'll look at the crossover separately. So each of these plots are just coming up right now. We're going to redisplay those plots after we get things normalized. Again, we've got that double in the density, and we'll also find that same type of effect. And all of those data sets are far more blurred out with the mixed lithologies. Not included in today's work was trying to relook at doing cluster analysis to see if we could break some of these classes into subclasses that would have more consistent lithologies and porosities. Again, with the DTC, with this double hump. So we'll just create those ones. We did some rescaling, such as taking the ROP. A lot of the data was directionally drilled with motors, so controlled drilling. And so what we really want to do in there is get a relative change. Did it speed up? Did it slow down? For this, we're actually just going to normalize each of the data zones by its percentile. Being geophysicists, I prefer VP over VS. We're just going to recalculate both of those, and we'll take a look again at them after we take a look at the after we move the residual. One of the larger items as well is the SP log. The SP log actually is heavily dependent on the mud conditions, and so we're actually just going to normalize it against itself and just take a look at what would be the residual. And then finally, if you remember, the bowl hole and the caliper ended up high. In reality, what we want to do is look more at the filter cake. And so, but we don't have bowl hole data everywhere, or the bowl hole size data. So we're basically just going to use the caliper to calculate out one of the more common bowl hole sizes to give an output, and then to calculate the filter cake. So in here, the black or darker lines are the actual bowl hole size, and the green is the ones that would be estimated from the red, which is the caliper. We've added that back in, but only added it back in when we didn't actually have the data. And so you end up with the bowl hole size. And we replaced here with whether or not it has a washout or whether or not it has porosity and filter cake. Want to do some additional work on this and take a look particularly on the washout for looking at, can we do machine learning analysis for determining bad hole. Nice thing with XGBoost, it actually handles that as just background noise. And so it doesn't actually affect its ability to create a training volume. It would have an effect though on doing a blind test analysis. Taking a set of removing the trend, created several routines. It takes a little bit of time. So I've commented it out. It takes about 20 minutes to run through on quite a number and then create the residuals, predominantly because I'm doing a depth shift for each well. That's in here, standardizing each attribute by well. That can take a fair bit of time. Because this is being marine data and it's off a shelf, there is a lateral shift because of different seafloor bed. I saved that out into a trend, and we'll just load that back in as if we had run it. And then we can actually just display that data. Again, everything looks fairly well conditioned, not really a lot of changes from the others. But when we take a look at those plots that we were doing before, and this will just take a little bit of a minute, you're going to see those double bumps have disappeared. If we had the actual density plot, you'd see everything basically is going to plot near or around zero, all of the logs, and that slant has been removed in some of the distribution. All of the, as we come in here, that double peak that we had seen before on the density log is now gone. And we're starting to see some better distribution of things like the coal out to one side, the limestone out to the other. Likewise, on the DTC, we had a double peak before. It's now down as a single peak. One of the things we need to look at is solving, because you'll see that the scatter is in the shallow part of the well is broader than at depth. And that makes sense if we're looking at really the P50 and the P10 values and how much broader they are. And as it gets more lithified, it gets more compacted. But that would be some future work. But really what we want to do is, has that improved XGBoost? And so just again here, just a quick check on what are the actual features we're going to use. Now in this case here, I've included the DTC and the P velocity log just to take a look to see if its importance has changed in its relative location. And if you remember before, the DTC was always held quite high up in the system. So In this case, after having both of them in there, they're basically equivalent. If we actually reran this and we put up here features drop, square brackets, sorry. No, I'll have to check and I'll have to remember how to do that later. If we actually, because we have both of them in here, it shows up if we actually drop it, one of the other ones will actually go up. And it turns out that the resistivity, the density, the velocities are our primary analytics. Things like the SP, the shear log, and that's purely because there's so little shear information in this well, less than 15%, ends up being quite low down. When we go through and actually take a look, our statistics continues to improve. We're now back up to 82%, but certain things like the dolomite, the limestone, the sandstone shale, the marl actually have low numbers, and that is somewhat to be expected because what they have provided us is really a mixed mineralogy in each of the lithoclasts, and what we're doing is a point-by-point analysis, which is in reality looking for mineralogy instead of lithology. Now, the most common thing, and when we actually did the contest, we did impute, and that's because things like decision trees, and all the rest of the different types of analysis requires it. This does take about a minute to run through, and we still have 13 minutes left, and then we're going to get right near the end here. The interesting thing is when we're imputing through on all the data, it's going to infill with, in this case, I've selected the median, but you could do the mean, most likely. There's a number of different, did test all the different ones. Bayesian ridge is being used in here, but did look through on the decision tree and extra tree, nearest neighbor. They all actually take longer to run. That's why for this, I've just left in the Bayesian ridge analysis. But it, in all cases, it actually reduces the overall performance, predominantly because we are having to put in one of the what's most common, which is going to be the shale. So it's going to it's going to feed into all of those gaps or NAND values. When we run through this, we ran it a little bit earlier. It took a little bit of time. It basically calculates out. It's really interesting. The VS, which was way on the bottom, has jumped way up in the analysis. And that's because, again, it's now being used as an indication of shale. And the statistics have actually gotten worse once again. And likewise, the overall stats within that. And that's pretty much the code I've put together just to kind of go through some of the thoughts of how we looked at trying to do the analysis, the one versed all, or taking a look at the feature importance to see relative positioning of each individual logs, etc. One of the big takeaways was the imputing actually degrades our answer. And it would now just be really time for any questions.
There is a question from Daniel de Oliveira. He said, thanks, David, for the presentation. Great job. brave to do a live code presentation. Nice, congratulations. Have you tried any other optimization technique instead of grid search to find the hyperparameters?
Not really. Originally, I was concentrating on this just going through the best feature engineering, and I actually did the grid search after Brian Russell asked the question at the Geo convention. And so no, I haven't done a different method.
So what I'm doing now, I'm allowing everybody to talk. So if you have a question, you can just ask now. You can just unmute yourself and ask. So feel free to ask any question.
For your imputing there, David, do you think like there's an alternative you can do to make the results actually beneficial to the machine learning process? Or
Yeah, it's actually what I'm going to try for my 699 project, is look at whether or not we can use regression. The disadvantage is you need to know the lithology beforehand. And
Right.
so that you're going to actually then substitute in the mean. When you actually then take it after training and use it against a data set, unfortunately, you don't have that knowledge to impute from. So the nice thing on XGBoost is it works without having to impute when all the other methods do require it. That's actually what the X stands for versus the gradient boosting, is how it deals with NAND values as well as the GPU.
Okay, that is another question from Kevin Fossenier. What about collinearity of some of the wireline logs?
It's a really good question in the sense that I realize that the keeping in things like the medium resistivity with the deep resistivity and the shallow resistivity ends up with a whole pile of duplication. And therefore, they actually end up showing up lower in the feature importance. And so I was always trying to take attention of that. And in the end, you'll see where I simplified down and combined the deep resistivity and the shallow resistivity into a single attribute, and just put the difference or the crossover in as a third one. So I do think from going through this, I can create more attributes and get a better fit. But when we were actually doing the validation, the results actually goes down. And so we're better off to really keep to the logs that we know have rock properties for the solution that we want to achieve. One of the next tests is to move this and use it against the Australian and New Zealand data, which has us that were available, and see how well it actually forecasts, how generalized it is.
Okay, thank you. Any other question? So if you don't have, once, sorry.
No, we should. I'm good to finish.
Go on. Okay, so if you don't have any more questions, so I'm just gonna finish now the presentation today. So thank you, David, for the presentation. It was very nice, very instructive. And remember that we make all those labs available in our YouTube channel, so you can watch later if you missed some part or if you didn't understand. Also, the code is going to be available in the Cruise website. So thank you, and don't forget to join us on social media to stay tuned for the next lab. Thank you.